Hi everyone, in this video we'll talk about antiderivatives and integrals like we've been discussing in class. So the concept of antiderivative is relatively simple. The concept of integral we're going to get to in a little bit, in a few minutes in this video. So antiderivative, the idea is a function, derivative of which is the function that you provided. So basically you're working backwards. Now you're given a function. How do you find a function that would be the antiderivative? And you can quickly check it. So, and the idea is basically very simple. So far we've just been taking derivatives, and let's say we're given a function, take the derivative, and you can figure out how something is decreasing or increasing and what is the rate of change. But what if we know the rate and we need to work backwards to find the original function or quantity or the amount and etc. So the concept of antiderivative function again is fairly simple. If we start with the antiderivative of a function that's relatively known as the derivative, let's say if f of x is 2x, think about which function would give us derivative 2x. Well, you can, if you override that solution x squared, it makes sense because the derivative is 2x and it matches, so you can always check it. But the solution would be right here. That's the capital F of x that we'll use. And if it's 3x squared, similarly, well, the antiderivative is x cubed, but this time we're going to add a constant, because if you think about it, it's going to be not just a single answer, but it's going to be a family of functions up to a constant, because you can add 5, for example, or subtract 100, or add 0.5, and so on. So constant could be anything, but because the derivative of it is 0, then we can actually, when we integrate or take the antiderivative, we can add a constant. And in a lot of applications, as we'll see, we're actually going to solve for that constant. So some other information would be given. So, and again, we can check it very quickly, and you can do that. And so from now on, we're always going to add a constant up until we get to the definite integrals, which will be section 6.4. Then we're going to do this a little bit differently. So again, some of the known ones, let's say 5x to the 4th, the antiderivative is x to the 5th plus a constant. And what if it's 1? Well, if you think about it, what if we try x plus a constant? Derivative of x is 1, and so that works. And again, you can check that. And let's jump to the power rule for antiderivatives. So basically, it's just like with derivatives. If your function is x to some exponent power, then the antiderivative, we're basically going to do it backwards. If for the derivative, we take the constant, the exponent down, and then we decrease it by 1. Well, in this case, for the antiderivative, we're going to increase the exponent by 1 and then divide by that number. And that's how we're going to get it, plus a constant. So let's say if it's x squared, you can pause the video, but if we increase the 2 by 1, if you note, you'll get x to the 3rd, and then we divide by that number over 3 plus a constant. And again, you can quickly check it. The derivative of x cubed is 3x squared, so 3 will cancel with a 3, and so you'll just get x squared, and as the answer, as you'll notice. What if it's x cubed? Well, you'll note antiderivative is x to the 4 over 4 plus a constant. What if we have negative exponents? We can approach them in the same way. Let's say if a function is 1 over x squared. We can rewrite it as x to the negative 2nd power, and then we can try the same thing. What if it's negative 2 plus 1? Then we'll get x to the negative 1 divided by negative 1 plus a constant, which if you divide by negative 1, we can basically, it's the same as multiplying by negative 1. You can pull it on the front right here. And we're going to do this for any negative numbers in denominator. And because originally we had a fraction, we can actually rewrite it as a fraction as negative 1 over x plus a constant. So we can do similarly with the negative exponents. And now let's use antiderivatives to define integrals. And that's what we're going to use from now on. So the idea of derivative was rate of change, how something is changing. But on the other hand, the idea of the integral, by definition, it calculates an area under the curve. It doesn't matter whether you're calculating cost, revenue, volume, whatever it is you're calculating, that the amount, let's say Facebook membership, whatever it is, it's always going to be area under the curve, or sum of areas of different geometrical figures. Let's take a look at, let me explain what's actually happening here. Let's say we're trying to figure out the area, the entire area under the curve. So if I, let me actually try drawing on here a little bit. Let's see if I can do this. For some reason, unfortunately, I'm not able to draw on the screen. So for now, just bear with me. But let's say if we try and figure out the area under the curve from A to B up to the x-axis, well, in general, it's not an easy problem, because if it's a general curve, it's not easy to calculate the area. But if we use this incredibly insightful technique that was discovered back in, I guess, 18th or 19th century, back when calculus was discovered. If we use a simple geometrical shape, it does not have to be a rectangle, but rectangle is by far the easiest, but it could also be trapezoid and a few other shapes. But let's say if we do use a rectangle, then if you note the way I drew it, the height of the rectangle is the actual function, whatever that point happens to be. We're going to be a little bit more specific later. And the width is, we'll call it dx. But if you're using a lot of those rectangles, then the width is going to be very, very small. So we will call it as dx delta x. So it actually becomes dx when it's small. So a single rectangle, the area would be length times width, which is f of x times dx. So this is just a single rectangle. But if you're adding all of them up, we'll see this in section 6.3, then it becomes a summation, or this integral sign, of f of x times dx. So it's actually the sum of all those areas of rectangles, and we can use 4, 5, 10, 200, probably with technology, and so on. Actually, the integral approximates infinitely many of them. It's actually limit as n goes to infinity, and we'll see this in section 6.4. So this whole chapter is being related to a single idea, and area under the curve. So we're going to use integral notation from now on. So now you know the S stands for sum, and f of x times dx. So the dx is the width of the rectangle, and f of x is the height, and that's basically relates to the area. But by fundamental theorem of calculus, we actually know that it equals to the antiderivative. It's just like with the limit definition of derivative. At the end, once the area is calculated, you'll note both the integral sign and the dx are gone. We're calculating, we're getting the final answer. And the final answer is the antiderivative, all by itself, plus a constant. When we'll start talking about definite integrals in section 6.4, we'll see another way to do this, but very similar. But for now, we're gonna talk about how do we do them in general, indefinite integrals. So if we see x cubed dx, well, what's the antiderivative of x cubed? Well, it's x to the 4 over 4 plus a constant. And that's the answer. And you'll note there's a lot of similar rules for integrals as they were for the derivatives, for the exception maybe of product and quotient rule and so on. But there is a constant multiple and sum and difference. Constant multiple, basically we're keeping the constant. You can pull it out of the integral, or you can keep it as you do the antiderivative, basically. So it would be k times antiderivative of f of x plus a constant. Sum and difference works the same way. You can separate them, and you can do them separately, basically term by term, as we're going to quickly find out. So let's take a look. For example, 2x to the 7th power, we're keeping the 2, that's the constant multiple, and it becomes x to the 8 over 8 plus a constant. And we can reduce the 2 with the 8, so it becomes x to the 8 over 4 plus c. What if I have negative 5? Since we're working backwards, a constant becomes the constant times x, because the derivative of it would be constant again. So it becomes negative 5x plus a constant. Again, if you check it, derivative of negative 5x is negative 5, so it actually works. So if you see a constant, then it actually becomes constant times x in that case. And here's another one, x squared minus 5x times dx. So x squared becomes x cubed over 3 minus, we retain this minus, 5x becomes, we keep the 5, x becomes x squared over 2, nothing to simplify here, and then plus a constant. Same thing with 21x plus 5x cubed, it becomes 21x squared over 2 plus 5x to the 4 over 4. There are a lot of fractions with integrals that you'll get, plus a constant. Similarly with negative exponents, x to the negative 6, well, we will actually get x to the negative 6. Remember, we're adding a 1 now, so negative numbers will decrease, or actually increase, but they will get smaller and closer to 0. And divided by negative 6 plus a constant. And we can simplify this. First of all, this negative we can pull out. You can keep it as x to the negative 6. I'm not sure why I put this in denominator. You can keep it as x to the negative 6, or you can put it in denominator. Either way would be fine. Now, power rule does not work for x to the negative 1, because if you increase it by 1, you'll get x to the 0 over 0. And it's not cool to divide by 0. We just cannot do it. So, what do we get? We have talked about this, but if you recall that the derivative of ln of absolute value, regardless if there's absolute value, but we're actually going to keep them to keep the same domain, equals to 1 over x. And so x to the negative 1 power actually becomes 1 over x. Here's the opposite of power rule. We actually want to rewrite it as 1 over x, or keep that in mind. And then it becomes ln of absolute value. If there is a constant on the front, then you'll just get constant in front of the ln. So that's how it works. Okay, so let's say if we see this problem, u squared minus u to the negative 1 becomes u cubed over 3, and then minus, so you can just keep that in mind, u to the negative 1 becomes ln of absolute value of u plus a constant. And similarly, 2 over u plus u over 4, well, you can rewrite it. I actually put it as u to the negative 1, so you can recognize that. You can keep it as u over 4 or pull it out. So sometimes it's necessary to simplify the original integral, sometimes it's not. So this step is actually, might be a little bit better to see, but not always necessary. And then 2u to the negative 1 becomes 2, ln of absolute value of u, plus, we keep 1 over 4, times u becomes u squared over 2. So you'll notice how the 4 and the 2 combine and they make it 8 plus a constant. And we also have integrals of exponential functions. E to the x is the easy one. It's just itself, just like the derivative. If you have e to the constant, which sometimes will show up, it basically reverse of the chain rule. You know, like if you take in the derivative, it would be e to the kx times the derivative of the exponent. And here is the opposite. Actually, in the next section, 6.2, we're going to see some of these. So it's e to the kx divided by the derivative of the exponent, which is just k. And again, it's opposite of the derivative. And this is where I'm explaining it. So this is the derivative. So finding antiderivative, you are going to divide instead of multiplying. And if it's a different basis, then again, instead of multiplying by ln, we divide by ln of the base. Okay, so you could try this. Negative 4 e to the x plus x over 3 actually becomes negative 4 e to the x, so it's itself, plus x over 3. It becomes x squared over 6. How did we get 6? Well, the 3 stayed, and it became x squared over 2. So 3 times 2 became 6. So that's how we get that. And similarly, if you have 5 e to the 0.01x, again, the 5 constant stays. And then you can divide it by the derivative of the exponent, 0.01x. That just becomes 0.01. And 5 divided by 0.01 is 500 e to the 0.01x plus c. This is good for some applications we'll do later. And here is basis other than e. So it's basically themselves, both of them divided by ln of the base. Okay, so fairly simple if you take your time to practice with them. And let's take a look at some quick examples. Let's say we have the marginal cost, 10 plus x squared over 100,000, and the fixed cost is 100,000. This information would be needed to solve for the constant later. And we need to find the cost function. So the cost function it's important to set this up. We know that the marginal cost is C prime of x. That's important to know that. It's the derivative of the cost. And so I'm setting this up as the integral. So this is the important step. Make sure to do this when you're working on the homework. Set it up as the integral of the function that's given to us times dx. It's important to follow that up with the dx. And then get the antiderivative, 10x plus, and it becomes, notice how did we get 300,000? Again, 100,000 stayed, and it becomes x cubed over 3, so it gets multiplied in denominator, plus c. But do not stop here. We do want to solve for the constant. We do not want to leave that. For the homework, it's important too, when you work on this one, definitely go back and think, what does fixed cost mean? Well, for us, it means C of 0. Before you actually purchase any items or produce any items, this is the upfront cost, so it's C of 0. If we have a polynomial, in this case, the function was 10x plus x cubed over 300,000. If you plug in 0, the only thing you'll have left is a constant, which does equal to the fixed cost. But be careful. If you have an exponential function, let's say e, then you're not going to get 0. So you may have to plug in x equals 0 and see actually what you'll have left over and so for it. So just be careful. But in this case, it is just a constant. Occasionally, you'll have this information. Let's say 5 items cost $50 to produce. So you'll have C of 5 equals to 50, and then you have to plug in 5 and solve for the constant. So just keep that in mind. So it's not that we're always given a constant. Sometimes we need to solve for it. And the actual cost function is 10x plus x cubed over 300,000 plus 100,000. And that's it, really. And here is a quick one about Facebook membership. When it was originally created at the start of 2005, Facebook had 1 million members already, probably from previous website. And since that time, the new members joined at the rate roughly, let's say this was discovered, so it's small m of t to stand for membership or rate of the membership, 3.2 t cubed minus 12t plus 10 million members per year. And we're talking about from year 0, which is since 2005, to 5 years from 2005 or up to 2010. Find the expression for Facebook membership capital M of t at time t. So note, we set it up as the integral. Make sure put this function in parentheses and times dt. Again, this is very important to set this up. Make sure to practice this for next exam. And how do we obtain this function? Well, just keep in mind, I'm actually given the final answer, but it's 3.2 t to the 4 over 4. 3.2 divided by 4, write this as a decimal. We'll actually get 0.8 minus 12t squared over 2. Actually becomes 6t squared over 2. The 10 becomes 10t, and then plus a constant. And once again, m of 0 right at the start, there was 1 million. We're just going to write it as 1, and keep in mind that it's in millions. And this is the actual function. Again, make sure you add the 1 to it. And for part B, use the answer in part A to estimate Facebook membership midway through 2008. Round your answer to the nearest 1 million members. Because our function is in millions, we can just round it to the nearest whole number. The actual figure was 80 million. We'll see how close we get. Well, if you note, the t is actually 3.5 midway through 2008. Again, keep in mind that it's midway, and we started at the start of 2005. And so midway would be 3.5 years since 2005. We plug in 3.5 into the function in part A. And I got 82.55 in my calculator. If you round it to the nearest whole number, we actually get 83 million subscribers. And that's it for this section.